So first and foremost, before we go any further, is there any questions on the last exercise set? Are you feeling comfortable solving for concentrations when given Ka and solving for Ka when given information? Feeling good about this? All right, cool. Let's move on. Oh, buffers. Okay, so this actually kind of dovetails really well into the next unit, but or the next subunit. But if you have any questions at all, let me know, because I want to talk about it today too. All right, so first and foremost, we talked about Ka yesterday. We talked about Kb yesterday. We talked about the beautiful square of the pH-POH and beautiful square of the pKa and the pKb and how they unite together. And all you need is a rice table and a concentration to get from one to the other. Hopefully that sounds familiar. So this is just basically more of the same, honestly. So once again, strong acids, Ka is, or the KEQ, Ka or Kb, for Ka for acids, Kb for bases. The KEQ is larger than 1, smaller than 1. And again, it's always going to be much larger than 1 to the point where it's entirely products, or can be considered entirely products, or much less than 1 to the point where the reactants don't change enough so that 2.5 minus X stays 2.5. You know what I'm talking about? Where you say 2.5 minus X is effectively 2.5 because the K is much smaller than 1. Okay, and again, I can't say for sure you're ever going to get a point for that, but do put it in just in case. Okay, so it's always one or the other. There's never going to be like nuance with this stuff. So anyway, so when you have a strong acid base, and this is exactly the same as Unit 4, when you have a strong acid base, they're going to react completely, one proton, one hydroxide. But what you need to do is get to moles. So this question is a review of Unit 4. So you have 250 milliliters of 0.35 molar HCl. So the HCl concentration is equal to the H plus concentration. You are mixing it with 150 milliliters of 0.5 molar NaOH. The NaOH concentration is the OH concentration. You reduce both to moles, find the limiting reactant, cancel out whatever the limiting reactant cancels out. Whatever's left over, you divide by the new volume. Can you bang this out in about 90 seconds? Give it a shot. Good. We did this in Unit 4. Let's do it again just to make sure we get the rest off. Gesundheit. Are you all done, Bennett?
I've got the moles of each, and then I'm gonna.
So whichever one is more, subtract the one that's less from it. Is that one out of charge?
Yeah.
Yeah.
Let's plug it in. I should just get been considering getting like a little USB thing, just like fold look. Kind of like what this does. This charges up from below. I can charge those from above. Okay, well, since you got the number of moles of hydronium, how many moles of hydronium do you have?
0.0875.
875. Can we get a confirmation on that?
Yeah.
Okay. And then how many moles of hydroxide do you have?
0.075.
75. Okay. So what we have here is the green is going to be the subtraction of the more, the less from the more minus the less, which leaves you how many moles in this case of what's the limiting reactant? The hydroxide, right? So the hydroxide is limiting reactant, and that means there's going to be some hydronium left over. So how much hydronium is left over in moles?
0.0125.
5. Okay. So that's moles of H plus remaining. Then you're going to take this number of moles, and you're going to divide it by what volume?
0.4.
Again, the total volume. And that's going to give you a concentration of the hydronium ion of what?
0.0313.
313? Yeah. Okay, cool. So now that we know the concentration of hydronium, we can find the pH and the pOH if we want to. So take the negative log of this, and we'll have our pH. 1.50. All right, cool. 1.50. Sounds good. Okay. So rust off. Ready to move forward? Okay. Any questions before we move forward? Moving forward. Come on, here we go. All right. So when this happens, when you get a weak acid strong base, something interesting happens. The acid proton, the protons in the acid, still react like a strong acid. And here is why. Even though in the reactants you have 1 million undissociated molecules, in the products you have 10 dissociated ions, every time a hydroxide reacts with a proton, another proton is made. Does that make sense? So you got 1 million over here, undissociated molecules. They're making 10 protons total. But every time a hydroxide comes in and reacts with that proton, another proton is made. React, proton, another proton. So you can basically do the same reaction. That means you have your MA, VA, molarity of the acid, volume of the acid, and then you have your MB, VB, molarity of your base, volume of the base, and in the middle is going to be moles. And again, it doesn't matter, numerically, it doesn't matter if they're strong acids or strong bases, or weak acids or weak bases, or weak bases, strong acids, weak bases. Because even if something is weak and there's a lot more undissociated molecules, when a hydroxide attacks a hydronium or hydronium attacks a hydroxide, another of those ions is created. And it just keeps doing that until all the protons are consumed or all the hydroxides are consumed. Is that clear? Okay. We're going to graph it later. What is important is the net ionic equation. For the net ionic equation for a strong acid, strong base, it's always going to be H plus OH minus makes H2O. It's always going to be that. Okay, so this is our strong acid, this is our strong base, and that's our water. However, for a weak acid or a weak base, you have to show the undissociated molecule because there's so much more of that undissociated molecule. So HNO2 is not a strong acid. HNO3 is. This is not nitric acid, it's nitrous acid. It's not HNO3, it's HNO2. It's not hydrogen nitrate, it's hydrogen nitrous. So what you're going to do is you're going to write the entire undissociated molecule representing the acid. If you want to put aqueous down there, you can, but you rarely need to. But the base is strong, so you're just going to write the hydroxide. How are we doing? Now, what should I put for the arrow? Should I use a single arrow or a double arrow? Read the question. Double arrow, because it says equilibrium. So we're going to use a double arrow. Then, of course, we're going to make our water. But we have to balance it. So what's left on the other side is NO2 minus. That is the net ionic equation for a weak acid, strong base. Cool? Example 2 does exactly the same. But then it says, okay, are we comfortable with this so far? Ben?
How are we supposed to know that HNO2 is a weak acid?
It's one of the few things you need to memorize in chemistry AP. That there are 6 strong acids, and they are HCl, HBr, HI, H2SO4, HNO3, and HClO4. So those are 6 strong acids you need to memorize of.
Okay.
I mean, like, in May, was it May 2nd or May 8th or whatever, just sit down and write those guys down on your test. Like, okay, one of the few things I need to memorize is there are 6 strong acids. All right, how we doing? Good. Okay, so there's equal volumes of 1 mole weak acid, sorry, 1 molar weak acid, and 1 molar strong base. Going to mix them together. And then what's going to happen is every hydroxide is going to react with a hydronium. Right? So eat, and there's equal volumes of equal molarity. So all the hydroxides are going to react with all the protons. Got to check something before, so I gotta check something so I don't mislead you. This is important. Don't really like to do that, but just I have what I think is going to happen, and then I have what I know is going to happen. I think this is the first thing. Click on task fires. There. Yes, it does.
Thank you.
All right. Just do that. Oh, that's a typo. Fine. Okay. Yeah, it is. It is what I thought it was going to be. Okay. So this is how it works. These are going to react, and they're going to keep reacting, keep reacting, keep reacting. And since the hydroxide is comes from a strong base, you have all the ions. There's no potassium. There's no potassium hydroxide left over. Cool. And then since the HNO3 or HNO2 is a weak acid, but it's reacting with a strong base, this hydroxide is going to eat all the hydroniums. So far, so good. So if you have 1 million of these and 1 million of these, you're going to make 1 million of these. And if you have 1 million of these and 1 million of these, you're going to have 1 million of these, and the other thing, you're going to have 1 million of, I'm going to put it in green, of the K plus. Now it's not in the net ionic equation, but it is in the beaker. So far, so good? Okay. Now, is there any hydroxide left over at equilibrium? Your gut says there is none, and there isn't. There's no hydroxide left over at equilibrium because they're equal. Are there any protons left over at equilibrium? No, because there's equal number of moles of protons and hydroxides, so all the hydroxides eat all the protons. Does water have a concentration? Not really. It is a liquid, so we pretend water doesn't have a concentration. I mean, the strict term for moles over liters, we can find it, but it doesn't have a concentration, which means the aqueous species, water is not an aqueous species, that have the highest concentrations are these guys. How do their concentrations compare?
Equal.
Very equal. Yep. Do they form potassium nitrous? Do they form KNO2?
No, they're disassociated.
Exactly.
They're ions.
The proton, the potassium plus one here, that keeps it from forming any kind of salt. No precipitate's going to form. Nothing is going to stay ions. There's the same number of NO2 ions as K plus ions. No precipitate will form, and they are equal. Is that clear? Can we move forward? Okay. Weak acid, strong base, again. Weak acid, strong base, again. Weak acid, strong base, weak acid, strong base. Come on, give us something else. Okay, this is great. This is the Henderson-Hasselbalch equation. Yeah. And it is actually, I think it still is given to you on your formula chart. It is, yep. It only gives you the acidic form of Henderson-Hasselbalch. If you look at equilibrium, at the bottom of the equilibrium box, you're going to see the Henderson-Hasselbalch only in the acidic form. Okay, what this is taking our beautiful squares and squishing them together, taking advantage of the fact that pH plus POH is equal to 14, and pKa plus pK, ahead of myself, pKa plus pKb is 14, which means pH plus POH equals pKa plus pKb. I don't know why I can't write pKb plus pKb.
What exactly is pKa? Sorry.
It is the negative logarithm of the Ka for that acid. And the Ka is the equilibrium expression for the HA acid that disassociates into H plus and A minus. So once again, for our acid, we say HA is in equilibrium with H plus A minus.
Yes.
Okay. And just like for bases, we have a Kb, and that is equal to the BH plus times the hydroxide ion concentration over B. And again, if you have the Ka for an acid, you automatically have the Kb for its conjugate. For instance, if your acid was HF, if you have the Ka for HF, then you have the Kb for NAF minus, or NAF, the F minus ion. And if you had the Kb for NH3, then you have the Ka for NH4 plus. Because these are the conjugates. Cool? Now, you never have to use the Henderson-Hasselbalch equation because it is a mathematical derivation which allows you to basically use a shortcut. And you're putting these things together with the pKa and the pH and all that, and you're basically taking part of it apart. And you're taking advantage of the fact that the logarithm of a product is the sum of those logarithms. But you're only taking the logarithm of half the equation. So you're leaving this part of the Ka equation aside. And for the Kb, you're leaving this part of the Kb equation aside. Actually, it's not. Kb is not up there. Okay, so far so good? So here's what I'm basically saying. If you have the Ka, you can get the concentrations, and the concentration will give you the pH. So you're going to get a pH by doing a negative logarithm of that. So far so good? So you're saying to take the logarithm of all this. Need more room. Can you imagine it's going over here? I'm going to take a logarithm of this. I'm going to go with negative logarithm of the Ka. And then I'm going to take the negative logarithm of all this stuff. But again, if you take the logarithm of a product, it becomes the sum of those logarithms. So you're going to say, all right, I'm going to go negative logarithm of the H plus ion, plus the negative logarithm of what's left over, and we're going to leave it left over. So this becomes pKa equals pH plus the logarithm of A minus over HA. Can you see it? Follow the math? I couldn't see it when I was your age, but I do now. Okay, now why is that cool? The reason this is really neat is if you know the pKa for an acid, then you know the pH as long as you know the ratio or the percent ionization. Remember, A minus over HA is percent ionization. So it's the logarithm of percent ionization. So if you know the percent ionization, then you know this ratio. Or if you know the HA and the percent ionization, you have the A minus. If you have the A minus and the percent ionization, you have the HA. Or if you have the A minus and the K, you get the idea? So you can basically say, all right, pH is going to equal to pKa as long as these two things are the same. If they're not the same and there's more A minus, your pH is going to be higher or lower if there's more A minus than pKa. So let's start. Let me rephrase this. Let's start with a situation where the A minus and the HA are equal to each other. Perfectly equal. So the A minus is equal to the HA. That makes this ratio what? This quotient, what does it make it?
1.
1. What is the logarithm of 1? No. 0. So the logarithm of 1 is 0. Yeah, give it a shot. Go logarithm 1. 0. That's the same reason like 10 to the 0 is 1. Anything to the 0 power is 1. Any logarithm of 1, natural or base 10, any logarithm of 1 is 0 because 10 to the 0 is 1. Or anything to the 0 is 1. You want to know why that is? Ask Mr. Strachan. He can break down the whole logarithm rules. I've known it and forgot it, so I don't care anymore. He probably still remembers. But the important thing is anything raised to the 0 power is 1. Therefore, any logarithm of 1 is 0. Huh? Cool. Okay. So understanding that, if the ratio of A minus to HA is 1, then the pH equals the pKa, which is really cool. Let me show you why. Let's draw on here. Imagine, imagine you had, you're going to graph the pH, and you're going to graph the volume of OH minus that you're adding. We're going to start with a beaker. And in this beaker, I need more room. In this beaker, you've got a whole bunch of H plus. And maybe you start with a pH of 1. So far, so good. And then you're going to add to it some base. So there's going to be some hydroxide that you're going to add to it. And the x-axis is going to be how much hydroxide you add. Volume of OH minus that you're adding. So far, so good. So imagine you have your beaker. Got your beaker. It's got a bunch of acid in it. You put your pH probe in it, and it says it has a pH of 1. Then you're going to slowly add base to it. The pH is going to do what? It's going to go up. And it's going to keep going up until something interesting happens. Well, this is what's happening. The HA in equilibrium with H plus A minus, as you add the, I keep getting the colors wrong, I apologize. This thing is so confusing. As you add the hydroxide, it's going to consume a proton. And this is the critical part. As it consumes a proton, the HA releases another one. Which means for a weak acid, you have a whole bunch of HA and no A minus. But as you add hydroxide, and a hydroxide absorbs a proton and it releases another one, it also releases an A minus. So as that happens, the HA concentration becomes the A minus concentration. So at the beginning of the reaction, okay, let me pause there. Do you see what's going on? So the hydroxide's coming in, it's eating the proton and setting it aside. Becoming a water molecule, I'm done, I'm out of the reaction. But every time that happens, the HA releases another H plus and A minus. So the HA concentration's going down, the A minus concentration's going up. Capiche? Okay, so if you looked at it, you're like, okay, down here, I have, about red. I have all HA. And it's going to react. It's going to make a curve that looks like this. It looks like this because you're graphing a logarithm. This is a logarithmic curve, logarithmic curve. At this point, right in the middle, you have all A minus and no HA. Down here, you have all HA and no A minus. Okay, so far so good. Well, that allows us kind of an interesting bit of math. I'm going to rewrite this in a second. Okay, are you ready? I'm going to flip this and rewrite the whole thing. I'm going to make a really neat graph. So let's make our graph. In our graph of pH versus OH added, we're going to start red. We're going to start here with all HA and no A minus. And then we're going to add hydroxide. And it's going to make a graph that looks like this. And at this point, there is no HA. There is all A minus. Good so far? If there's no HA left, it's all A minus. Are there any protons left? Exactly, there is none. So this is a neutral point, and it has a name. It's called the equivalence point. It's called the equivalence point. The point at which you have consumed all of your protons by adding hydroxide is called the equivalence point, because that's the point where this happens. rest of the curve is where you're adding hydroxide, and you have more hydroxide than you're just going to keep adding hydroxide. It's not going to react with protons anymore. The protons are gone. If you keep adding, then you're going to have the rest of this curve. So if you were to label it, you'd be like, down here, this is acidic. Up here, this is basic. Because here, the hydroxides are consuming protons. And here, you're adding hydroxides and there's no more protons to consume. How are we feeling? Okay, now here's the beauty of the Henderson-Hasselbalch equation. Would you get along with the punchline? At the halfway point, between here and here, this is called the perfect buffer. Because at the perfect buffer, the A minus concentration equals the HA concentration. You have all HA and no A minus here. Yeah, I'll finish writing down, and don't you do that? I'll explain the punchline once you finish writing stuff down. And I get a drink of a beverage. Talking makes my throat hurt. Okay, so at this point down here, you have all HA, no A minus. Up here at the equivalence point, you have all A minus, no HA. At the exact halfway point, you have equal HA and A minus. It's a perfect buffer. And at the perfect buffer, at that point, the A minus equals the HA, the pH equals the pKa. Usually I do it on the whiteboard, so I have plenty of room. Let me draw a similar graph over here. Okay, so let's look at the pH. Down here, pH is low. Up here, the pH is high. At the equivalence point, the pH, at the halfway equivalence point, the pH equals the pKa. So far, so good? At every zone in here, before the halfway point, is the pH higher or lower than the pKa?
Would it be lower?
It's lower, yep. So below this point, the pH is less than the pKa because you have more HA. And you are taking a log, I didn't even write the, oh, right here. It's right here. There's the Henderson-Hasselbalch equation. So before that halfway point, you have more HA, which means this number is going to be less than 1, and the logarithm of less than 1 is a negative value. So you are subtracting pH, right? So it's less. Okay, that's backwards. pH plus pH. pH. That's Henderson-Hasselbalch. Okay, anyway, so here, this is a lower value. Oh, sorry, this is more. The fraction is less than 1, so you are reducing the pH, it's pKa minus something. And above that halfway point, from here to here, the pH is larger than the pKa. Because now your numerator is larger. You're taking a logarithm of something more than 1, so you are adding pKa plus something equals the pH. Right? Okay. Then it just becomes a number, like how much is left over. But the concept is the most important part. All right. If you're comfortable with all this stuff, give me a thumbs up. If you have any questions, now would be a great time to ask. All right. Bye, my screen. All right. If you want to make a perfect buffer, which is what we're going to do next week. Yeah, next week. If you want to make a perfect buffer, all you do is you put both those things in the same solution. Just give you a little preview. I'm going to make a buffer. So what I'm going to do is, here, see this right here? To make a perfect buffer, what you need is an acid and its conjugate base. can make a perfect buffer by using a base and its conjugate acid. You just dump A minus and HA in. And then you basically create a solution of pH that you want. And that's what we're gonna do next week. I'm gonna give you a number and an acid, and you are going to create a solution that has an exact pH that you want by just doing math. That's for next week. All right, we got strong base, added bit of good. Okay, so we're gonna come back to, I'm gonna make sure I've checked all the boxes before we start doing any more exercises. Equal volumes, yep, okay. Yeah, right, that equation, identify the species of highest concentration. I think pH of the final linear reactant, okay. More of the same, 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 lots and lots of practice. Okay, it's more of the same, it's more of the same. Okay. This is going to be interesting because this is going to basically, we're going to use the Henderson-Oswald equation to say how much is left over of everything. Let's go back to this. Whoa, let's go back to this one. Yes, okay, this is a big one. Yeah, this is good. Okay, this is great. So this is great for a couple of reasons. First and foremost, acetic acid has 3 ways to write it, and it's super annoying. Acetic acid is HC2H3O2. It's also that, where that's the proton. Because acetic acid is this molecule. It is what's called a carboxylic acid. All carboxylic acids have this functional group at this end of the molecule. This is methyl carboxylic acid. There's ethyl and propyl and so on. It just has a fancy name called acetic acid. So yeah, that's also the way you can write it. And that's the way that AP writes it sometimes. It's really annoying. There's a third way. I'm not going to show you. Actually, shoot, you can figure it out. What's the third way to write it down?
C2H4.
Yeah. My favorite, because it puts the proton in front. But every now and then you see it written this way and this way. Sometimes chemistry is just funky. Okay, well, speaking of funky, look at this. We're going to take a strong base of KOH, and we're going to add it to a weak acid of acetic acid. The pKa acetic acid is given to us. We need to find the final pH. Well, we know, it's like, hey, it gave me the pH and the pKa. I'm going to use Henderson-Hasselbalch. You're like, equals the pKa plus the logarithm of A minus. It's on the formula chart, so I freaked out, but it's okay, because the formula chart saved me. pH is what I'm looking for. pKa I have. Now I need to get these guys. How am I going to do that?
We have the volume and the molarity, so you can solve for the moles, right?
That's exactly right. And here's the trick. There is going to be an equal number of A minus as OH. Why is that?
Oh, because it's at equilibrium. Yeah, the point of sound we're looking at, right?
Yes, but why is it that there's going to be an equal amount of A minus as OH?
It's a weak acid, strong base.
And what does the hydroxide do?
Takes all the
And leaves behind
An A minus.
an A minus. So we need to figure out, we need to make sure that there is more acid than there is base. Well, 50 milliliters, 3 molar, 20 milliliters, 1.5 molar, there's clearly going to be more acid than base. But here's the beautiful thing. This concentration equals the concentration of the OH. Because every hydroxide that eats an H plus from the HA leaves behind an A minus. Yeah? And then this one is going to be the concentration of A minus minus the the concentration of HA originally. So let's rice it. Need to write it down anyway. We have HA. Our HA is going to disassociate into H plus A minus, and originally we have how much HA? 50 and 3, so that's 0.150 moles. Check my math. Is 3 times 0.05 0.15?
Yes.
Okay, so there's the moles, and we're doing over a volume of 70.070 liters.
$2.14.
2.14 molar?
0.214.
Okay, I was like, wait a minute. 0.214. That's more like it. Molar. Cool so far? All right. So we have the 150 molar HA to begin with. But the hydroxide comes in like, I'm going to kill you. I'm going to eat some of your protons. So hydroxide comes in, and you are going to lose, the change is going to be how much hydroxide you get eaten. How much hydroxide is available to get eaten in moles? 1.5 times 0.02.
0.03.
0.030 moles of hydroxide. In other words, this is the number of moles we're going to start with HA. This is going to be how much hydroxide the HA is going to change by. And then this is going to be plus the same amount, but we don't care about it because it's going to be eaten by the hydroxide. The one we do care about is this one. Okay. 0.05 times 0.002, 0.030. Yeah, cool. Okay, so subtract. So the ending concentration is going to be 0.150 moles minus 0.030 moles, all over 0.070 liters. Don't care about hydronium. A minus is going to be 0.30 moles, all over 0.070 liters. There's our A minus, there's our HA. Oh, but it gets even better. Because what we care about is the concentration of HA over the concentration, or over the concentration of A minus over the concentration of HA. These have something in common. What is it? Well, you think about it, all right, you think about it.
They're equal.
What's equal? They're not equal because we are not at the halfway point that we know of. Ta-da! If you want to do each of them separately, you totally can, and then just divide. Or you can realize, do I have the same volume? Do I have the same denominator in each case? So this becomes 0.150 moles minus 0.030 moles. I got them upside down. Oh, I got them upside down. I'm so sorry. I got them upside down. This is 0.030 moles minus 0.0. This is 0.150 moles minus 0.030 moles, all over 0.070 liters. That is the HA. Our original original HA minus the change that hydroxide ate over the total volume, and then this one is 0.30 moles over 0.70 liters. 0.070 liters. And you're like, hey, there's the same denominator in both cases. So you get to cancel them out. You do. So if you want to do the whole molarity over the whole molarity, that's perfectly fine. If you want to cancel them out, that's fine too. So the ratio becomes 0.30 moles. That's the A minus that was created over 0.150 minus 0.030 moles. That's the HA that's left behind. And you're going to take the logarithm of that. I don't know what it is. You're doing it. So pH equals 4.8 plus the logarithm of 0.150 minus 0.030 over 0.030. Oh, I did it again. Jeez. You gotta catch me. You're gonna be like, Mr. Barr, you made a giant mistake. Okay. Alexa, stop. 0 over 0.150 minus 0.030.
4.2.
4.2? Perfect. Can we get a confirmation on that?
Yeah.
So here's how we check our work. Did we consume half of the HA, so the A minus and the HA are equal? Did we consume half of the protons available? The protons available is 0.150. Did we consume half of those protons? Nope. We only consumed that. Half of it would have been 0.075, right? So we didn't consume half, which means our pH should be less than the pKa. And it is. If we consumed more than half, then the pH would have been higher than the pKa. All right. Anyone else feel steam coming out?
Yeah.
I'll call it a day. Any questions before I turn off the video and say bye-bye to Canyon? Hope you had a good trip, Canyon.
Why is HA equal HA minus A minus?
At the equilibrium point, at the half equivalence point, all of the HA, so we start with a bunch of HA. We consume A minus, we're leaving an A minus behind. We start with HA. We consume H pluses, leaving an A minus behind. So we start with a whole bunch of HA. We go to no HA, all A minus. But at the exact halfway point, we have consumed half of the H pluses, leaving half A minus. So we have a whole bunch of HA, half the HA and half the A minus, and then all A minus. Those two sums are always going to be one number of moles, because we're starting with a bunch of HA, we're ending with a bunch of A minus. At the halfway point, we have the same amount of A minus and HA. Does that answer your question?
Yeah.
I'll make sure that's answering the question you were asking. Oh, here we go. Bye, Canyon. Hope you had a great trip.